Imagine holding a single teaspoon of something in your hand, something so unimaginably heavy that it weighs 1 billion tons. That's not science fiction. That's the reality of a neutron star, one of the universe's most extreme and mysterious objects. These cosmic powerhouses are born from the collapse of giant stars, and they pulse with rhythms that carry secrets about the nature of reality itself. Carl Sagan once said, "The cosmos is within us. We are made of star stuff." And in many ways, understanding neutron stars is like listening to the heartbeat of the universe, a rhythm that connects us to the vast, beautiful, and often violent processes that shape everything we see and everything we are. Neutron stars are the collapsed cores of massive stars that have ended their lives in spectacular supernova explosions. In their final moments, these stars compress matter so intensely that atoms themselves break down, squeezing protons and electrons into a sea of neutrons. What's left is an object no bigger than a city, yet containing more mass than our Sun. But it's not just their incredible density that captivates scientists and dreamers alike. It's their pulse, the steady, rhythmic beat that some neutron stars emit across space like cosmic lighthouses. These pulses are far from random. They are precise, reliable, and packed with information. They allow us to test the laws of physics under conditions so extreme they cannot be replicated anywhere on Earth. They let us probe the nature of gravity, matter, and even the fabric of spacetime. So why does this matter to us? Because hidden within those pulses are answers to some of humanity's biggest questions. Where did we come from? What is the universe made of? How do matter and energy behave under pressures and densities beyond imagination? In this video, we're going to journey into the minds of stars, decoding those pulse patterns, understanding what they tell us, and discovering why neutron stars are more than just distant curiosities. They are messengers carrying stories from the farthest reaches of space and time. So get ready. We're about to dive deep into the hearts of these celestial giants, where every pulse is a whisper from the abyss and every rhythm a clue waiting to be unraveled. Now, let's rewind the cosmic clock to witness the very beginning, the spectacular and violent birth of a neutron star. It all starts with a star much more massive than our own Sun, a true giant burning through its nuclear fuel at a ferocious rate. For millions of years, it shines brilliantly, fusing hydrogen into helium and creating heavier elements in its core. But this powerful engine can't run forever. Eventually, the star exhausts its fuel, and the delicate balance between the outward push of radiation and the inward pull of gravity suddenly shatters. What happens next is one of the most energetic events in the entire universe. A supernova explosion. The core of the star, no longer supported by the energy from fusion, collapses catastrophically under its own immense weight. In less than a single second, this core, which was once the size of a large planet, is crushed down into an unimaginably dense sphere only about 12 miles across. To put that into perspective, imagine taking all the mass of our Sun, which is over 300,000 times more massive than Earth, and squeezing it into a space smaller than most cities. The forces at work here are almost beyond comprehension. The collapse is so violent and the pressures so extreme that it fundamentally alters the very building blocks of matter. Electrons are literally forced into protons, creating a vast, swirling ocean of neutrons. This is why we call them neutron stars. They are essentially gigantic atomic nuclei, each one a city-sized ball of neutrons. This whole process is a stunning demonstration of physics in its most extreme form. Quantum mechanics, the rules that govern the subatomic world, plays a crucial role in halting the total collapse just short of forming a black hole. It's a phenomenon called neutron degeneracy pressure, a quantum law that says you can't pack neutrons infinitely close together. They need their space, and this resistance is the only thing stopping the star from vanishing into a singularity. Astrophysicist Jocelyn Burnell, whose pioneering work led to the first discovery of a pulsar, perfectly described these objects as nature's most perfect laboratory. They are places where matter is pushed into states we could never hope to recreate in any lab on Earth. The temperatures are in the billions of degrees, magnetic fields are trillions of times stronger than Earth's, and the density is so high that a single sugar cube-sized piece would weigh as much as a mountain. These incredible objects are more than just cosmic curiosities. They are fossil records of the universe's most violent moments. The elements forged in their birth and scattered by the supernova explosion are the very seeds of new solar systems. The iron in your blood, the calcium in your bones, much of it was created in the heart of a dying star and blasted across space by an explosion just like the one that creates a neutron star. By studying them, we are effectively reading a history book of the cosmos, one that tells the story of how the raw materials for planets and life itself came to be. Understanding their violent origin is the essential first step to decoding the rhythmic messages they send us. But what exactly are these pulsars, and how do they speak to us across such vast distances? Think of a lighthouse standing tall on a rocky coast, its powerful beam cutting through the darkness, sweeping across the water in a steady, predictable rhythm. To a ship far out at sea, that light appears as a periodic flash, a pulse of light against the blackness. Now, imagine that same principle on a cosmic scale. A pulsar, which is a highly magnetized, rotating neutron star, acts like that lighthouse. It emits powerful beams of radiation, not just light, but often radio waves, X-rays or gamma rays from its magnetic poles. And here's the crucial part. Those magnetic poles are usually not aligned with the star's axis of rotation. This misalignment means that as the neutron star spins, these beams sweep through space, much like the beam from a lighthouse spins around its central lamp. If our planet happens to lie in the path of that sweeping beam, we detect a brilliant, fleeting flash of energy with every rotation. We see a pulse, and these aren't just any flashes, they are astonishingly regular. The timing of these pulses can be so precise that they rival the best atomic clocks we have ever built here on Earth. Some pulsars maintain their rhythm for years, even decades, with a stability that is almost incomprehensible. This isn't a random, chaotic signal. It's a structured, repeating pattern, a true language of rhythm and timing emanating from the heart of a collapsed star. So, what are scientists listening for in this rhythmic language? Everything. The primary pulse, the main heartbeat, tells us the star's rotation rate. Some neutron stars spin sedately, completing a single rotation every few seconds. Others, known as millisecond pulsars, are cosmic speed demons, whirling around hundreds of times every single second. But the information goes far deeper than just the basic spin. By studying tiny, subtle changes in the timing of these pulses, shifts of mere microseconds, researchers can decode a wealth of information. They can measure the immense strength of the star's magnetic field, which can be trillions of times stronger than Earth's. They can detect a gradual slowing of the spin, which reveals how the star is losing energy over time. They can even sense the presence of planets orbiting the pulsar, as their gravitational tug causes minute periodic delays in the arrival time of the pulses. The discovery of this cosmic language in the late 1960s was a revolution in astronomy. When Jocelyn Burnell first detected those strangely regular pulses, she and her advisor initially nicknamed the source LGM for Little Green Men. because the signal was so precise it seemed almost artificial. Once it was understood to be a natural phenomenon, a neutron star, it opened up entirely new ways of observing the universe. Suddenly, astronomers had the most precise clocks imaginable scattered across the galaxy. They could use them as tools to test Einstein's theory of general relativity with incredible accuracy by watching how the pulsars were affected by gravity in binary systems. They could use them to study the interstellar medium, the thin gas and dust between the stars, by observing how the pulsars were scattered and delayed as they traveled through it. This rhythmic language gave us a direct line into the physics of the most extreme environments in the cosmos, allowing us to peer into the internal structure of these stars and understand the violent neighborhoods they often inhabit. But among the diverse family of neutron stars, there exists a class so extraordinarily powerful and volatile that they stand in a category all their own: Magnetars. If a typical neutron star is a cosmic powerhouse, a magnetar is that same powerhouse plugged into a grid of unimaginable energy, possessing a magnetic field so intense it defies easy analogy. To even begin to grasp its strength, consider this: the magnetic field holding a simple fridge magnet to your kitchen appliance is a gentle whisper. Earth's own protective magnetic field is a steady, reliable hum. The field around a magnetar, it is a continuous, universe-shaking scream. We're talking about magnetic fields that are 1,000 trillion times stronger than Earth's levels of magnetism, so extreme that they begin to warp the very vacuum of space itself. At such phenomenal strengths, the laws of physics as we know them start to behave in bizarre and fascinating ways. This magnetic force is so potent that if a magnetar were located halfway between the Earth and the Moon, a distance of about 190,000 miles, its magnetic field would effortlessly erase the information from every credit card on our planet. But the real danger lies far deeper than that. This incredible force is powerful enough to distort the shape of individual atoms themselves, stretching them from their usual spherical form into long, thin, needle-like rods. It's a fundamental alteration of matter from a distance of thousands of kilometers, a testament to a force that truly governs its domain. This unimaginable energy doesn't just sit idly by, it builds up until it must be released. And when a magnetar decides to release it, the universe pays attention. These stars are known for sudden, violent eruptions called starquakes. Think of it like the tectonic activity on Earth, but on a scale that is almost comically more powerful. The crust of a magnetar, an immensely dense and rigid structure, can suddenly fracture and shift under the immense strain of its own magnetic field. When it does, it unleashes a cataclysmic burst of energy in the form of X-rays and gamma rays. In a single second, one of these flares can release more energy than our sun will emit over 100,000 years. The flash is so brilliant that even from tens of thousands of light years away, it can temporarily outshine every other gamma ray source in the entire sky, including the entire rest of the galaxy. On August 27, 1998, a magnetar flare was so powerful that it actually ionized Earth's upper atmosphere, disrupting long-range radio communications. Our planet was physically affected by an event that occurred 20,000 light-years away. The study of these incredible outbursts has been pioneered by scientists like astrophysicist Krisa Kuvaliatu. Her meticulous work in analyzing the light curves and energy signatures of these flares provided the first conclusive evidence that magnetars were a distinct class of object. By studying the afterglow of these explosions, researchers can peer into environments that are otherwise impossible to replicate, conditions where nuclear physics, quantum electrodynamics, and the behavior of matter in relativistic plasmas all converge. These flares act like a sudden, brilliant flash of lightning, illuminating the intricate physics at play on and within the star's surface for just a few precious moments. Unlike the steady, metronomic ticking of a typical pulsar, the pulse patterns from a magnetar are often wild and unpredictable. Their rhythms are punctuated by sudden glitches, random bursts, and long periods of silence, making them the erratic geniuses of the neutron star world. This very unpredictability is a goldmine for scientists. Each glitch and flare is a data point, a clue about the internal structure of the star. The way the star recovers from a starquake, for instance, can tell us about the viscosity of the superfluid soup in its interior and the tensile strength of its solid crust, the strongest material in the known universe. By watching these magnetic monsters strain against the very laws of physics, we are actively testing our understanding of how matter and energy behave under the most extreme conditions imaginable, constantly pushing the boundaries of what we believe is possible. Now, let's take this idea of cosmic rhythm to its grandest possible scale. Imagine you could turn the entire galaxy into one giant scientific instrument, a detector so vast it could sense the faintest whispers of the universe itself. This isn't a fantasy, it's the incredible reality of pulsar timing arrays. We've established that individual pulsars are like perfect celestial metronomes, their pulses arriving with breathtaking regularity. But what if you listened not to one, but to dozens, even hundreds of them, all at the same time? You would no longer just be hearing individual heartbeats. You would be listening to a full cosmic symphony, and within its harmonies, you could detect the deepest, most subtle notes in the universe, the ripples in spacetime known as gravitational waves. The concept is as brilliant as it is elegant. Scientists carefully select a network of extremely stable millisecond pulsars distributed across the sky. This array acts like a galaxy-sized net. Each pulsar is a single node in this net, its steady pulse acting as one strand. For years, sometimes decades, radio telescopes like the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia meticulously record the arrival time of every single pulse from every single one of these pulsars. The precision required is almost beyond belief. We're talking about measuring differences in arrival times down to the nanosecond. That's a billionth of a second. To put that into perspective, a nanosecond is to 1 second what 1 second is to about 31.7 years. Now, imagine a gravitational wave passes through our region of the galaxy. Predicted by Einstein over a century ago and directly detected for the first time in 2015, these waves are literal distortions in the fabric of spacetime, caused by colossal events like the merging of supermassive black holes. As this wave passes through, it does something extraordinary. It very, very slightly stretches and compresses the space between Earth and the pulsars in the array. This minuscule distortion, this cosmic wobble, changes the distance the radio signals have to travel by a tiny amount. For one pulsar, the pulse might arrive a few nanoseconds early. For another, it might arrive a few nanoseconds late. By themselves, these tiny shifts in individual pulsars could be written off as noise. But when you look at the correlated pattern across the entire array, the way many pulsars seem to shift in a coordinated way, a clear signal emerges from the noise. It's the fingerprint of the gravitational wave itself. This is the monumental work of projects like NanoGrav, the North American Nanohertz Observatory for Gravitational Waves. After analyzing over 15 years of data from dozens of pulsars, the collaboration announced in 2023 the first compelling evidence for a gravitational wave background, a constant, low-frequency hum permeating the universe, likely created by the combined chorus of millions of pairs of supermassive black holes orbiting each other in the hearts of distant galaxies. This isn't the sharp chirp detected by ground-based observatories like LIGO. This is the deep, resonant bass note of the cosmos, a sound so low its wavelength can be measured in light years, and its frequency takes years to complete a single cycle. This achievement transforms our understanding of what astronomy can be. We are no longer just using telescopes to collect light. We are using the intrinsic timing of dead stars as the most precise gauges ever conceived to measure the warping of the universe itself. It confirms a key prediction of general relativity on a scale Einstein himself might never have imagined, and opens a completely new window onto the cosmic web, allowing us to listen in on the dynamics of black holes so enormous they govern the evolution of entire galaxies. By decoding the subtle rhythms of these neutron stars, we have built a key to unlock phenomena that are otherwise completely invisible, turning the galaxy into our laboratory and its oldest stars into our most reliable guides. So what is it actually like inside one of these cosmic powerhouses? We've talked about their precise pulses and incredible magnetic fields, but the true mystery lies buried deep within, under layers of matter crushed into forms we can barely imagine. The interior of a neutron star is the most extreme environment in the known universe, a place where the rules of physics are pushed to their absolute limit. The densities here are so immense that they exceed even the nucleus of an atom. A single sugar cube's worth of this material would weigh billions of tons, and the temperatures can soar into the billions of degrees. It's a realm of such profound pressure and heat that matter itself is forced into states that simply cannot exist anywhere else, not even in the most powerful particle colliders on Earth. To unravel this mystery, scientists have become cosmic detectives, using the star's own pulse patterns as their primary clue. This technique is surprisingly similar to how seismologists study the interior of our own planet. When an earthquake rumbles through the Earth, the way seismic waves travel and reflect tells us about the layers of the crust, the mantle, and the core. Neutron stars have their own version of earthquakes, aptly named Starquakes. These are sudden fractures in the star's incredibly dense, rigid crust, which is under unimaginable strain from the powerful magnetic fields and the rapid spin. When one of these starquakes occurs, it causes a tiny but detectable change in the star's rotation, a timing glitch. One moment the pulse is perfectly steady, and the next the star has stuttered, spinning just a fraction of a second faster before settling back into its rhythm. These tiny glitches are like secret messages from the star's heart. The way the star recovers from this event, the speed and manner in which it settles back down, reveals critical details about what's inside. It tells us about the rigidity of that solid iron crust, which is likely 10 billion times stronger than steel. More importantly, it provides evidence for what lies directly beneath it, a superfluid sea of neutrons. This isn't a fluid like water, it's a quantum superfluid, a substance that flows with absolutely no friction or viscosity. Think of it like this: if you were to stir a cup of this neutron superfluid, it would literally swirl forever. The interaction between this bizarre, frictionless interior and the solid, brittle crust is what causes these rotational hiccups, giving us a direct probe into conditions that are otherwise completely hidden from view. But the true frontier of this research lies even deeper, in the very core of the neutron star. This is where physics ventures into the realm of the truly speculative and extraordinary. Theories based on quantum chromodynamics suggest that under such insane pressure, the neutrons themselves might break down into their constituent parts, a soup of free quarks and gluons known as quark-gluon plasma. This is a state of matter that hasn't existed freely since the first microseconds after the Big Bang. Other models propose the existence of hyperons, exotic particles that contain strange quarks, which are normally incredibly unstable and decay almost instantly. But inside a neutron star, the pressure is so immense that these exotic particles could be stable, forming the very foundation of the core. Pioneering researchers like astrophysicist Anna Watts are at the forefront of this exploration. Her work involves using incredibly sensitive X-ray telescopes, like a NICA instrument mounted on the International Space Station, to study the surfaces of neutron stars. By carefully measuring the X-ray pulses coming from hotspots on the surface, she and her team can map the star's size and mass with unprecedented accuracy. This data is then fed into massive supercomputer simulations that model the equation of state, the complex relationship between pressure and density for the matter inside. It's a painstaking process of comparing the models to the real-world observations, slowly narrowing down the possibilities of what the core could be made of. Understanding what happens in the heart of a neutron star does far more than just satisfy our cosmic curiosity. It directly advances our knowledge of nuclear physics, helping us understand the strong force that holds all atomic nuclei together. It reveals how matter behaves under pressures so extreme that they warp the very rules of particle interactions. Every new observation, every refined model, brings us closer to answering fundamental questions about the building blocks of our universe and the forces that govern them. By decoding the secrets locked within these ultra-dense orbs, we are not just studying distant stars, we are testing the very laws of nature under conditions that we can never hope to recreate on Earth. It was the late summer of 1967, and a young doctoral student named Jocelyn Burnell was meticulously analyzing reams of data from a new radio telescope she had helped build. The project, led by her advisor Anthony Hewish, was designed to study the twinkling of distant quasars, a phenomenon caused by the solar wind. The data came in on long, continuous rolls of chart paper, and Bell's job was to scrutinize miles of these squiggly lines by hand, looking for any anomalies. It was painstaking, tedious work, a testament to the often unseen labor that underpins great discoveries, and then she saw it, a faint, peculiar signal, a little bit of scruff, as she later called it, that didn't look like anything else. It was a series of pulses, perfectly spaced about 1 1/3 seconds apart, arriving with a regularity that was utterly unnatural. The signal was so precise, so clock-like, that the most logical explanation seemed to be that it was artificial. In a moment of scientific humor mixed with genuine bewilderment, she and Hewish half-jokingly labeled the source LGM-1 for "little green men." The notion that they might have stumbled upon a beacon from an extraterrestrial civilization was a thrilling, if unsettling, possibility. They kept the discovery secret for weeks, checking and rechecking the equipment, ruling out any terrestrial interference or malfunction. But then Bell found another one in a completely different part of the sky, pulsing at a different rate. You might find one alien civilization, but finding two made it statistically improbable. The signals had to be natural, a new type of astronomical object never before seen. They had discovered pulsars. The announcement of the discovery sent shockwaves through the astrophysics community. Here was a phenomenon that defied all existing categories. The pulses were far too rapid to come from something as large as a star. Conventional wisdom held that stars simply couldn't vibrate that quickly without flying apart. The true eureka, a moment came when theorist Thomas Gold proposed the correct model, a rapidly spinning, ultra-dense neutron star. This was the missing piece. The lighthouse model we discussed earlier perfectly explained the pulses. The incredible density of a neutron star provided the mass, and its small size allowed it to spin so fast without disintegrating. In that single brilliant insight, a theoretical prediction from the 1930s was finally confirmed. Neutron stars were real. The significance of this discovery cannot be overstated. It was the first direct observational evidence for the existence of neutron stars, transforming them from a speculative idea in a physics textbook into a tangible, observable reality. It opened an entirely new window on the universe, one built on timing and precision rather than just imaging. Almost immediately, astronomers realized these objects were gifts from nature, the most perfect and stable clocks imaginable, placed strategically throughout the galaxy. They became tools for testing the laws of physics in ways that were previously impossible. Yet, the story of the pulsar's discovery is also a poignant chapter in the history of science, one that raises important questions about recognition and credit. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle, the head of the radio astronomy group, for their decisive role in the discovery of pulsars. Jocelyn Burnell, the researcher who first noticed the scruff on the chart, who diligently followed up on it, and who played an integral part in the discovery, was not included. The decision was controversial then and remains a topic of discussion today, often cited as a classic example of how the foundational work of junior researchers, particularly women, can be overlooked by the highest accolades. Burnell herself has always handled the situation with remarkable grace and perspective, noting that the culture of the time meant that students were almost never recognized in such a way. Rather than becoming embittered, she has used her platform to tirelessly advocate for greater inclusion and equity in science. Her story is a powerful reminder that scientific progress is rarely the work of a single isolated genius. It is a collaborative, often messy human endeavor, built on the curiosity and persistence of many. It's a narrative that adds a deeply human dimension to the cold, precise rhythms of pulsars, connecting our quest for knowledge to our ongoing struggle to recognize every contributor fairly. This foundational moment didn't just give us a new class of object to study, it gave us the very tools and the motivation to start decoding the universe's most rhythmic secrets. But if you thought the steady beat of a typical pulsar was impressive, prepare to meet the true athletes of the neutron star world, the millisecond pulsars. These are not your average cosmic timekeepers. These are the speed demons, the ultra-marathon runners spinning at a pace that defies easy comprehension. We're talking about neutron stars that complete entire revolutions not in seconds, but in mere milliseconds. Some of them spin over 700 times every single second. To put that into a perspective you can almost feel, imagine the blade of a high-powered kitchen blender. Now imagine an object with more mass than our entire sun spinning hundreds of times faster. The centrifugal forces at their surfaces are so immense that if it weren't for the overwhelming gravitational pull holding them together, they would literally tear themselves apart. So how does a massive, collapsed star become such a dizzying cosmic top? The prevailing theory is a fascinating process of stellar recycling. It begins with a neutron star in a binary system, orbiting a companion star. Over millions of years, the immense gravity of the neutron star begins to pull material, mostly hydrogen and helium, off the surface of its companion. This stolen matter doesn't just fall directly onto the surface. It forms a vast, swirling disk of superheated plasma, known as an accretion disk, that orbits the neutron star like the rings of Saturn. As this material from the inner edge of the disk finally rains down onto the neutron star's magnetic poles, it releases a tremendous amount of gravitational energy, creating brilliant hotspots that we see as X-rays. But crucially, this incoming matter doesn't just bring energy, it brings angular momentum, the same physics that makes an ice skater spin faster when they pull their arms in. With each atom that strikes the surface, it gives the neutron star a tiny, tiny push, a minuscule spin up. Over hundreds of millennia, this constant torrent of matter acts like a gentle but persistent hand, accelerating the star's rotation from a stately few revolutions per second to a mind-numbing blur. This entire transformation fundamentally changes the star's nature. The same accretion process that spins it up also seems to dampen its once ferocious magnetic field, burying it under the accumulated material. The result is an object that is not only incredibly fast but also astonishingly stable and quiet. Their pulses arrive with a metronomic consistency that surpasses the best atomic clocks humanity has ever built. This legendary precision is what makes them indispensable tools for some of the most sensitive experiments in all of physics. They are the cornerstone of pulsar timing arrays, those galaxy-scale gravitational wave detectors we discussed earlier. By monitoring the subtle, correlated shifts in the pulse arrival times from an array of these millisecond pulsars, scientists can detect the faint ripples in spacetime caused by the slow, cosmic dance of supermassive black holes millions of light years away. Perhaps no other system demonstrates their power more beautifully than the double pulsar, a breathtaking cosmic laboratory discovered in 2003. This isn't just one pulsar orbiting a companion. This is a system with two active pulsars orbiting each other every 2.5 hours. It's an incredibly rare and precious configuration. By meticulously timing the pulses from both stars as they whip around each other at a fraction of the speed of light, astronomers can test the predictions of general relativity with unparalleled accuracy. The intense gravitational field causes the orbits to decay as they radiate energy away in gravitational waves, and the timing measurements have confirmed Einstein's predictions to within a staggering 0.05%. It's a resounding validation of a century-old theory, delivered by the precise ticks of these two celestial clocks. Studying these recycled speed demons does more than just test fundamental physics. It tells a profound story of stellar evolution and survival. It shows that a neutron star is not necessarily a static tomb at the end of a star's life. Through interaction and partnership, it can be reborn, gaining a new lease on life and a new purpose in the cosmic ecosystem. Their existence illustrates the dynamic, ever-changing nature of the universe, where even the most extreme objects can evolve, adapt, and become something entirely new through relationship and the relentless flow of cosmic time. Just as a cardiologist studies the unique pattern of a heartbeat on an EKG to assess the health of a human heart, astrophysicists perform a similar kind of diagnosis on neutron stars by meticulously analyzing their pulse profiles. This isn't just about timing the interval between beats, it's about reading the intricate shape of each individual pulse. Every pulsar's profile is a one-of-a-kind signature, a complex waveform that acts like a cosmic fingerprint, encoding a wealth of information about the star's most intimate details: its size, the geometry of its powerful magnetic field, the precise physics of its emission mechanisms, and even the environment it's moving through. The process of building this profile is a monumental exercise in patience and precision. You can't just look at a single pulse, it's far too faint and noisy. Instead, scientists must collect thousands, even millions of pulses over months or years of observation. They then use sophisticated algorithms to fold all of this data, aligning each pulse perfectly on top of the others, averaging out the random noise of the universe to reveal the pristine, underlying signal. It's like taking 1,000 slightly blurry photographs of the same subject and stacking them to create one perfectly clear, high-resolution image. This resulting pulse profile is the star's true, unmistakable voice, cleansed of all interstellar static. Once they have this clean profile, the real detective work begins. The shape of the pulse, its width, the number of peaks, the symmetry of its rising and falling edges paints a detailed picture of the emission region at the magnetic poles. A simple, single, sharp peak might suggest a relatively small, well-defined hotspot. A broader, more complex profile with multiple components could indicate a more intricate magnetic field structure or the presence of two polar caps coming into view. By tracking how this profile changes over time, sometimes over decades, researchers can detect incredibly subtle phenomena. For instance, a gradual shift in the profile structure can reveal that the star itself is slowly wobbling on its axis, a process known as precession, much like a spinning top beginning to slow down. This analytical power extends far beyond the star itself. The pulse profile can also act as the most sensitive detector imaginable for uncovering a pulsar's cosmic companions. As a planet orbits a pulsar, its gravitational tug causes the star to wobble in a tiny, predictable orbit. This minute motion alternately stretches and compresses the distance the radio signals have to travel to reach Earth. The effect isn't on the pulse's timing alone. It can actually cause a measurable distortion in the very shape of the pulse profile itself as our viewing angle to the emission region changes slightly. It was through this meticulous profile analysis that the very first planets outside our solar system were discovered orbiting the pulsar PSRB 1257+12 in 1992, a landmark finding that proved planetary systems could exist in the most extreme environments imaginable. To get the full story, scientists can't rely on a single telescope or wavelength. They must engage in a coordinated multi-wavelength campaign, a kind of astronomical task force. A pulsar's profile might look one way in radio waves, but completely different in X-rays, where we see the thermal glow from the actual surface of the ultra-hot magnetic poles. By combining these vastly different views from observatories like the Chandra X-ray Observatory and the vast networks of radio dishes, researchers can build a comprehensive, three-dimensional model of the star. They can map the temperature distribution across its surface, understand how particles are accelerated to near light speed along magnetic field lines, and even detect the presence of debris disks, the remnants of a companion star it has devoured. Each pulse profile is a chapter in the star's biography, and by learning to read this fine print, we are slowly compiling the life stories of these incredible celestial objects. But to truly grasp the power of these cosmic laboratories, we need to witness them in action, and there is no better example than the story of the Hulse-Taylor binary pulsar. Discovered in 1974 by Russell Hulse and Joseph Taylor, this system is not just a pair of stars, it is a gift from the universe, a perfect natural experiment for testing the most profound predictions of Einstein's general relativity. It consists of two objects orbiting each other in a tight, frantic dance. One is a pulsar, its radio beacon flashing with metronomic precision, and the other is almost certainly another neutron star, a silent but massively influential partner. The key to the entire experiment lies in the precision of that pulsar's clock. As the two incredibly dense stars whip around their common center of mass at a significant fraction of the speed of light, the pulsar's signal becomes a detailed probe of the warped spacetime between them and us. When the pulsar is on the far side of its orbit, moving away from us, its pulses are stretched out, arriving at our telescopes with a slightly longer delay. When it swings around to the near side, moving towards us, the pulses are compressed, arriving a tiny bit sooner. By meticulously mapping this pattern over years, astronomers could reconstruct the entire orbit with astonishing accuracy. But they noticed something else, something far more significant than a simple orbital path. The orbit itself was slowly, inexorably shrinking. The two stars were spiraling closer and closer together at a rate that exactly matched what Einstein's equations predicted. This orbital decay is the smoking gun for gravitational waves. According to general relativity, any two massive objects accelerating through spacetime will radiate energy away in the form of these ripples. This energy loss causes the system to slowly lose orbital energy, leading the stars to spiral inward. The Hulse-Taylor pulsar provided the first indirect but utterly compelling evidence that gravitational waves were real. The orbital period was decreasing by about 76 millionths of a second per year, a minuscule amount, but one that was perfectly measurable thanks to the pulsar's exquisite timing. It was a direct confirmation of a key prediction made 6 decades earlier, and it earned Hulse and Taylor the Nobel Prize in Physics in 1993. This single binary system transformed gravitational waves from a theoretical curiosity into an observable phenomenon, paving the way for the direct detections we have today. Beyond the orbital decay, neutron stars in binary systems also allow us to observe other subtle relativistic effects. One of the most elegant is called the Shapiro time delay, named after the astrophysicist Erwin Shapiro who first proposed it. The theory is beautifully simple. Light, or in this case a radio pulse, will take longer to travel through a gravitational field than it would through flat space. The gravity of a massive object literally slows down the passage of time itself, causing a delay in the signal. In a binary pulsar system, this effect is most pronounced when the pulsar's signal passes very close to its companion star on its way to us. As the pulses skim through the deeply curved spacetime around the companion, they are delayed by a predictable amount. By carefully measuring this delay, scientists can actually weigh the companion star and measure the orbital inclination with incredible precision, providing yet another stringent test of general relativity that it has passed with flying colors. These experiments are not just about confirming what we already know, they are about probing the very boundaries of our understanding. General relativity has been spectacularly successful, but physicists know it is not the final word. It famously does not play well with quantum mechanics, the other pillar of modern physics. The intense, strong field gravity around neutron stars is the ultimate testing ground to see if Einstein's theory begins to show any cracks. Are there any deviations from its predictions in these most extreme environments? Could there be hints of new physics, perhaps extra dimensions or new particles, that subtly alter the behavior of gravity? By pushing the measurements to ever greater precision, using newer and more exotic binary systems like the double pulsar, scientists are essentially stress testing the theory to its absolute limit. In this way, neutron stars are far more than distant objects of curiosity. They are active, functioning laboratories that we can observe from millions of light years away. They provide the strong gravity, the high velocities, and the perfect clocks we need to conduct experiments that are impossible in any Earth-bound facility. By decoding their rhythmic pulses, we are not just studying stars, we are interrogating the fundamental force of gravity itself, exploring the nature of space-time, and seeking answers to questions that lie at the very heart of our understanding of the cosmos. Even the most precise cosmic clocks occasionally stutter. After years or even decades of flawless metronomic ticking, a pulsar can suddenly, without warning, spin faster. For a fraction of a second, its rhythm is broken. Its pulse arrives a tiny bit earlier than expected, and then, over days or weeks, it gradually slows back down to its original steady pace. Astronomers call these events glitches, and they are among the most fascinating and perplexing behaviors observed in neutron stars. They reveal that beneath the seemingly calm and predictable exterior of these stellar corpses lies a turbulent and wildly exotic interior, constantly in a state of dynamic struggle. To understand what might be happening, we need to picture the internal structure of a neutron star. Think of it as having three main components. The outermost layer is a solid crust, perhaps a kilometer thick. This isn't crust like on Earth. It's a crystalline lattice of atomic nuclei, overwhelmingly iron, packed together with incredible density and held in a rigid structure that is likely the strongest material in the entire universe. Beneath this incredibly strong crust lies the inner crust, a transition zone where atomic nuclei begin to dissolve into a sea of free neutrons. And then, at the very heart of the star, is the core. This is the most mysterious region where physicists believe the neutrons themselves might break down into a soup of free quarks, a state of matter known as quark-gluon plasma. Now here's where it gets truly strange. Much of the interior, particularly the inner crust and core, is thought to be a superfluid. A superfluid is a bizarre state of matter that exists only at extremely low temperatures and has zero viscosity. It flows without any friction whatsoever. If you were to stir a cup of neutron star superfluid, it would never stop swirling. This superfluid is also peppered with tiny tornado-like structures called quantized vortices. Normally, these vortices are pinned or locked to the crystalline lattice of the solid outer crust. Because the superfluid has no friction, it wants to keep spinning at a constant rate, while the solid crust, which is slowly losing rotational energy and breaking over millennia, is gradually slowing down. This creates a rotational lag between the two components, a kind of internal tension. The leading theory for what causes a glitch is a sudden and catastrophic unpinning of these vortices. Imagine the superfluid is like a vast, placid lake held behind a dam, the dam being the pinning force of the crust. The pressure builds and builds as the crust slows down, and the superfluid wants to keep spinning fast. Eventually, the dam breaks. A vast swarm of these microscopic vortices suddenly breaks free from the lattice and surges outward. When they move, they carry with them their immense angular momentum, and they transfer this spin energy in a sudden rush to the solid crust. It's like a figure skater pulling their arms in very suddenly, causing them to spin faster. The entire star experiences a tiny but measurable speed up a glitch. There's another compelling model that could explain some glitches, a starquake. Even though the crust is immensely strong, it is not invincible. The neutron star's powerful magnetic field, which is frozen into the crust, exerts unimaginable strain on this solid shell. Furthermore, as the star spins down over its life, its shape changes slightly. It becomes more spherical. This change puts tremendous stress on the rigid crust. Occasionally, this stress becomes too much to bear, and the crust fractures a starquake on a truly epic scale. When this happens, the star's moment of inertia changes slightly, and just like that figure skater again, it spins faster to conserve its angular momentum. The result is the same observed glitch, but born from a different, equally violent internal process. Studying these events is like performing remote ultrasounds on an object thousands of light years away. The way a neutron star recovers from a glitch tells us everything about its internal composition. A fast recovery suggests a loosely coupled interior where the different components can quickly resynchronize. A slow, gradual recovery points to a high-viscosity environment, perhaps with different layers of superfluid sliding past each other. The size and frequency of the glitches give us clues about the strength of the crust and the number of vortices that can be pinned. Each glitch is a data point, a tiny flash of insight into a realm of physics we can never hope to visit. Some neutron stars, like the Vela Pulsar, are famous for their relatively predictable, large glitches that occur every few years. Others are completely erratic, with some experiencing frequent micro-glitches and others going silent for decades before a major event. This variability suggests that the internal structure of neutron stars might not be uniform. Some might have thicker crusts, others might have more turbulent superfluids, and the exotic matter in their cores might behave in ways we haven't even theorized yet. This unpredictability is a constant reminder that for all their precise regularity, neutron stars are still dynamic, living objects, hiding a storm of incredible forces just beneath their surface, and every stutter is a message from that hidden world. While the solitary neutron star is a fascinating object, its story becomes infinitely richer and more dynamic when it finds itself in a cosmic partnership. A remarkable number of these stellar remnants are not alone. They are locked in a gravitational dance with a companion star, creating a binary system that becomes a powerhouse of high-energy physics and cosmic revelation. This companion can be almost anything: another neutron star, a dense white dwarf, or even a more typical main sequence star like our own Sun. It is within these intense gravitational relationships that some of the most spectacular and informative phenomena in the universe unfold. The drama begins with the neutron star's immense gravity, which acts like a cosmic vacuum cleaner. If the stars are close enough, it begins to violently pull material, mostly hydrogen and helium, right off the outer layers of its companion. This stolen matter doesn't fall straight down. Instead, it forms a vast, swirling, superheated disk of plasma called an accretion disk, orbiting the neutron star like the rings of Saturn set ablaze. As this material spirals inward from the inner edge of the disk, it finally plummets onto the neutron star's surface at its magnetic poles. The energy released in this impact is staggering, heating the surface to millions of degrees and causing it to glow brilliantly in X-rays. This is how we detect many of these systems, classifying them as X-ray binaries. But the incoming matter does more than just create a flashy light show. It carries with it the energy of angular momentum, acting like a gentle but persistent hand that spins the neutron star faster and faster. This is the very process that creates the millisecond pulsars we discussed earlier, taking a slowly spinning relic and reviving it into a dizzying cosmic top. Sometimes the accretion of this fresh hydrogen and helium onto the neutron star's surface leads to events of even greater violence. As new material piles on, the layer at the bottom is subjected to ever-increasing pressure and temperature. Eventually, the conditions become so extreme that it triggers runaway nuclear fusion. In a breathtakingly short instant, the accumulated fuel ignites in a titanic thermonuclear explosion that flashes across the entire surface of the star. From our vantage point thousands of light-years away, we see this as a sudden, brilliant spike in X-rays, a phenomenon aptly named an X-ray burst. In just a few seconds, one of these bursts can release more energy than our Sun will emit in an entire week. These flashes are not just spectacular, they are crucial laboratories. By studying their light curves and spectra, scientists can probe the physics of nuclear fusion under conditions of extreme gravity that are impossible to replicate on Earth, teaching us about the fundamental reactions that create the elements around us. The most profound consequence of these binary partnerships is not what happens during their dance, but how it ultimately ends. As the two stars orbit each other, they radiate energy away in the form of gravitational waves, those subtle ripples in spacetime predicted by Einstein. This slow but steady energy loss causes their orbits to decay, drawing the stars inexorably closer together over hundreds of millions of years. Their fate is a final, catastrophic merger. On August 17, 2017, the world's gravitational wave observatories, LIGO and Virgo, felt the unmistakable tremor of such an event: two neutron stars colliding in a galaxy called NGC 4993, 130 million light-years away. This event, known as GW 170817, was a watershed moment in astronomy. For the first time, we not only heard the gravitational wave chirp of the inspiral, but also saw the corresponding flash of light across the electromagnetic spectrum, from gamma rays to visible light to radio waves. The aftermath of that collision confirmed one of the grandest theories in astrophysics, that the universe's heaviest and most precious elements are forged in these incredible cosmic smash-ups. The brilliant glow that followed the merger, called a kilonova, was the telltale signature of rapid neutron capture process, or the R process. In the energetic debris ejected from the collision, neutrons were captured by atomic nuclei at an astonishing rate, building up elements heavier than iron in a matter of seconds. Spectroscopic analysis revealed the unmistakable fingerprints of newly created gold, platinum, and other rare earth elements, finally providing the long-sought origin story for these metals. It meant that the gold in a wedding ring or the platinum in a catalytic converter was likely born in the violent merger of two ancient stellar corpses billions of years ago. These cosmic duos illustrate that relationships, even between stars, are engines of creation and destruction, driving the chemical enrichment of the entire cosmos and literally seeding galaxies with the building blocks of planets and potentially life itself. Now let's experience these cosmic rhythms not as data points on a graph, but as sound. Scientists have taken the precise radio pulses from neutron stars and translated them into something we can directly perceive: sound waves. This process, called sonification, transforms the abstract into the auditory, letting us actually hear the heartbeat of the cosmos. It's a powerful shift in perspective. Where once we only saw a spike on a chart, we can now listen to the steady, rhythmic ticking of a pulsar millions of light years away. For example, the pulses from the famous crab pulsar, when sped up to a frequency our ears can detect, create a sound remarkably similar to a human heartbeat, a deep, reassuring, and constant thump-thump that has continued unabated for nearly 1,000 years since the supernova that created it was witnessed from Earth. Other pulsars produce more complex patterns. Some sound like rapid metallic clicks, like a Geiger counter detecting a radioactive source, while others have a more melodic, almost musical quality with double peaks or drifting tones. This isn't just done for public spectacle, though that is a wonderful benefit. Sonification is a legitimate scientific tool that offers a unique way to analyze data. Our ears are exceptionally good at detecting subtle patterns, rhythms, and irregularities that our eyes might gloss over when staring at vast datasets. A researcher listening to years of pulsar data might pick up on a tiny, almost imperceptible hiccup in the rhythm, a micro glitch, or a moment of nulling where the pulse briefly vanishes. That could have been lost in the visual noise of a plot. It's a different mode of perception, allowing intuition and auditory processing to work alongside traditional statistical analysis. This approach has proven so valuable that it's used in other fields, from seismology to medicine, where listening to data can reveal nuances that sight alone cannot catch. Beyond the lab, the sound of pulsars has become a profound tool for connection and outreach. Astronomy is often a visual science dominated by stunning images from telescopes. Sonification opens a new door, making the universe accessible in a different way, particularly for those who are blind or have low vision. It allows everyone to engage with the wonder of a neutron star on a sensory level. Museums and planetariums often feature these sounds in their exhibits, creating immersive experiences where visitors don't just learn about the precision of nature but feel it, hearing the unwavering rhythm of a celestial clock that has kept perfect time for millennia. It transforms the pulsar from a distant, intellectual concept into a relatable, almost intimate phenomenon. We are hearing a real signal that has traveled across the galaxy to reach us, a message in a rhythm that we can understand on a primal level. This creative fusion of art and science highlights a deeper truth about our quest to understand the universe. The drive to sonify data is born from the same curiosity that inspires a musician to compose a symphony or a poet to write about the stars. It is a desire to experience and express the beauty and order of the natural world. By listening to the cosmos, we are participating in a timeless human tradition of seeking harmony in the world around us. The steady pulse of a neutron star is a rhythm written into the fabric of spacetime itself, and for a moment, by converting it into sound, we are not just distant observers but active participants, tuning into the grand, rhythmic symphony of the universe. But what if these cosmic lighthouses could illuminate something even more mysterious than gravity or nuclear matter? What if they could help us detect the most elusive substance in the universe, dark matter? This might sound like science fiction, but it's a captivating and serious area of theoretical physics. Dark matter, which makes up about 85% of all matter in the cosmos, refuses to interact with light, making it utterly invisible to our telescopes. We only know it's there because of its gravitational pull on galaxies and galaxy clusters. For decades, scientists have built elaborate detectors deep underground, hoping to catch a fleeting glimpse of a dark matter particle. But what if we already have the perfect detectors scattered naturally throughout the galaxy? What if they are neutron stars? The premise is as elegant as it is profound. Neutron stars, with their unimaginably strong gravitational fields, could act as immense traps for dark matter. As a neutron star moves through the galaxy, it would continuously sweep through the vast halo of dark matter that is believed to surround us. If dark matter particles, known as WIMP or other theoretical constructs, interact even minutely with normal matter, they could be gravitationally captured by the neutron star. Over billions of years, these particles would accumulate in the star's incredibly dense core. The sheer number of particles involved is staggering. A single neutron star could potentially capture an amount of dark matter equivalent to the mass of an entire asteroid, all from particles that individually weigh almost nothing. This accumulating mass could have two potential and dramatic effects. The first is a subtle change in the star's internal properties. As dark matter particles collect in the core, they might occasionally annihilate with each other, releasing energy. This extra energy input could slightly slow down the neutron star's natural cooling process, a rate that astronomers can already measure by studying the temperature of its X-ray emissions. An anomalously warm old neutron star could be a tantalizing hint that something is heating it from within. Even more precisely, the additional mass of all those captured particles, though small, could infinitesimally alter the star's moment of inertia. This would manifest as a tiny, yet potentially measurable, change in its rotation rate over long periods, a deviation in the pulse timing that cannot be explained by standard spin-down models. The second possibility is far more extreme. If certain types of dark matter particles exist that can collapse under their own gravity, a critical mass accumulating in the core could trigger a catastrophic phase transition. In this speculative scenario, the dark matter core could suddenly collapse in on itself, converting the entire neutron star into a black hole. From the outside, it would appear as if a perfectly stable, ticking pulsar simply vanished from the sky without a trace, leaving behind only the quiet hum of empty space. While no such event has ever been observed, the mere possibility pushes the boundaries of our imagination and shows how neutron stars can be used as natural laboratories to test the wildest frontiers of particle physics. Of course, this remains highly speculative. Researchers are not claiming to have found dark matter in this way. Instead, they are using the exquisite precision of pulsar timing to set limits on the properties of dark matter. The fact that we observe millisecond pulsars that are billions of years old still ticking away with unwavering stability, places stringent constraints on how much dark matter can be accumulating inside them. If dark matter interacted too strongly, these stars would have shown anomalies or disappeared long ago. Their very existence rules out certain theoretical models, guiding particle physicists toward more plausible candidates. This is a beautiful example of how astronomy and particle physics converge. We are using the largest possible experiments, stars themselves, to probe the smallest possible particles, turning the entire galaxy into a canvas for discovering the fundamental rules of our universe. It demonstrates that the tools for next-generation discovery might not always be here on Earth. Sometimes they are already out there, spinning in the dark, waiting for us to learn how to read their messages. The tools we have today are already incredible, but the next generation of observatories and supercomputers now on the horizon promises to transform our understanding of neutron stars from informed deduction into something closer to direct observation. We are standing at the precipice of a new golden age of discovery, powered by instruments of such sensitivity and scale they would have been unimaginable just a few decades ago. Leading this charge is the Colossal Square Kilometre Array, or SCAR, an international mega-science project that is not so much a single telescope as a revolutionary network. When its thousands of radio antennae across South Africa and Western Australia are fully operational, the SKA will form a collecting area of over 1 square kilometre, making it the most sensitive radio telescope ever constructed by a staggering margin. This immense power will be directed towards the galactic plane in a systematic, all-sky pulsar survey of unprecedented depth. Current telescopes have catalogued around 3,000 pulsars. The SKA is expected to discover tens of thousands more, effectively mapping the Milky Way's population of these stellar remnants. But it's not just about quantity, it's about quality. The SKA's phenomenal sensitivity will allow it to detect pulsars that are too faint or too fast for today's instruments, including the elusive sub-millisecond pulsars, whose very existence would push the limits of our understanding of neutron star physics. More importantly, the sheer precision of its timing measurements will be breathtaking. The SKA will be able to measure the arrival time of pulses with an accuracy down to a few tens of nanoseconds over several years. This isn't just an incremental improvement, it's a quantum leap that will supercharge pulsar timing arrays, allowing us to move from simply detecting the gravitational wave background to actually mapping it, pinpointing the individual supermassive black hole binaries that create this cosmic hum, and listening to the symphony of the universe in high fidelity. While radio telescopes like the SKA listen to the precise ticks, a new generation of X-ray observatories will be watching the fiery surfaces. The Advanced Telescope for High-Energy Astrophysics, or Athena, is a mission being developed by the European Space Agency with a planned launch in the 2030s. Athena's powerful X-ray optics and advanced spectrometers are designed to do for high-energy astronomy what the James Webb Space Telescope has done for the infrared. It will study neutron stars with a focus on their thermal emissions, the actual heat radiating from their surfaces, and the scorching hotspots at their magnetic poles. By performing detailed X-ray spectroscopy, Athena will be able to measure the gravitational redshift on the surface of a neutron star with unparalleled accuracy. This single measurement, how much the star's immense gravity stretches and reddens the light escaping from its surface, will directly tell us the ratio of its mass to its radius, a fundamental property that has been notoriously difficult to pin down. Knowing this for a variety of neutron stars will finally allow physicists to rule out entire families of equations of state, telling us definitively whether their cores are made of neutrons, hyperons, or free quarks, and solving one of the longest-standing mysteries in astrophysics. But even the most powerful telescopes are limited to observing the outside of these stars. To truly see within, we need another kind of tool entirely, the supercomputer. The extreme conditions inside a neutron star involve a complex and chaotic interplay of general relativity, nuclear physics, plasma physics, and superfluid dynamics, a problem so computationally intensive that it has been largely out of reach until now. The latest exascale computers, capable of performing a quintillion calculations per second, are finally allowing scientists to create three-dimensional, high-resolution simulations of these incredible environments. Researchers can now model the violent merger of two neutron stars in stunning detail, tracking the creation and ejection of heavy elements in the resulting kilonova. They can simulate the sudden unpinning of superfluid vortices that causes a glitch, or the crust-shattering strain of a Magnetar starquake. These are not just animations, they are sophisticated numerical experiments that incorporate our best theories of physics. When the results of these simulations are compared against the real-world data from telescopes like the SETI and Athena, we enter a powerful feedback loop. The simulations make predictions that the telescopes can test, and the observational data then refines and improves the models, driving us ever closer to a complete and self-consistent theory of matter at its absolute limit. The questions these next-generation tools are poised to answer are as profound as they are exciting. They will help us finally determine the true nature of the enigmatic state of matter squashed into a neutron star's core. They will unravel the precise mechanisms that generate those lighthouse beams of radiation at the magnetic poles, a process involving particle acceleration and plasma physics that we still don't fully understand. And on the grandest scale, they will allow us to use neutron stars to conduct the most stringent tests yet of general relativity, potentially revealing whether Einstein's theory holds firm in these most extreme gravitational fields, or if we begin to see the subtle fingerprints of new physics. The future of neutron star research is not just about building bigger telescopes. It is about synthesizing information across the electromagnetic spectrum and combining it with revolutionary computational power to solve puzzles that have persisted for decades. We are building a unified toolkit to decode the universe's most extreme phenomena, and with it, we are preparing to write the next chapter in our understanding of the cosmos. It's easy to let our imaginations run wild when we contemplate the vast and violent cosmos, and neutron stars, with their almost unimaginable extremes, are often cast as the villains of deep space. A common and understandable fear is that one of these ultra-dense objects could, like a cosmic vacuum cleaner, suddenly swoop into our solar system and devour our planet. While this makes for thrilling science fiction, the reality is far less dramatic and much more reassuring. The nearest known neutron star is Calvera, located over 250 light-years away. To put that into perspective, that's over 6,000 times the distance between our Sun and Pluto. At such a vast remove, its gravitational pull on our solar system is utterly negligible, no more significant than that of any other star of similar mass. Even if one were to pass closer, a neutron star's gravity is only dangerously overwhelming if you venture extremely near it, well within the orbit of the Moon. The emptiness of space is our greatest protector. The chances of a random neutron star barreling into our celestial neighborhood are so astronomically low that they are effectively zero. These objects are not predatory monsters lurking in the shadows. They are distant, fascinating laboratories, and understanding their true nature allows us to replace fear with genuine awe. Another popular misconception stems from their most famous feature, their incredible timing. We often hear that pulsars are nature's most perfect clocks, and while that is true for many, This reputation can create the false impression that they are infallible metronomes, ticking away with machine-like perfection for all eternity. The truth is far more interesting. Many pulsars do exhibit astonishing stability, but they are not immune to showing their personality. We've already discussed glitches, those sudden spin-ups that reveal the turbulent superfluid dynamics raging in their interiors. But some pulsars engage in an even more baffling behavior known as nulling. For reasons that are not fully understood, a pulsar's beam can simply switch off. Its rhythmic pulses vanish from our telescopes for periods that can last from a few rotations to hours or even years, only to suddenly and unpredictably switch back on again as if nothing happened. This isn't a sign of a broken clock, it's a clue. Scientists believe nulling may be caused by sudden shifts in the star's magnetosphere that temporarily disrupt the complex process generating the radiation beam. These imperfections and anomalies are not flaws in our understanding. They are vital data points, helping us piece together the intricate and dynamic physics that govern these incredible objects. We also tend to simplify their origins, comfortably categorizing all neutron stars as the remnants of spectacular supernova explosions. While this is the primary pathway, nature often finds alternative routes. There is a compelling theory that some neutron stars, particularly those that appear isolated and without a supernova remnant, may be born in a much quieter, though no less dramatic, process known as accretion-induced collapse. Imagine a white dwarf, the Earth-sized core of a less massive star in a binary system. If it is actively pulling matter from its companion, it can eventually accumulate so much mass that it surpasses the Chandrasekhar limit, the maximum mass a white dwarf can support against its own gravity. Instead of triggering a standard type Ia supernova, this overloaded white dwarf might bypass the explosion entirely and collapse directly into a neutron star. It's a silent, sudden birth, leaving behind a neutron star without the fiery stellar funeral pyre we typically associate with their creation. This possibility reminds us that the universe is full of surprises and that our models, while powerful, must always leave room for these fascinating exceptions to the rule. Dispelling these myths is not just an academic exercise, it is a crucial part of scientific outreach. When the public understands that neutron stars are not imminent threats, but distant objects of profound beauty and scientific value, it transforms them from subjects of fear into catalysts for curiosity. This demystification is a primary goal of efforts like this very video. By replacing sensationalism with substance, we can foster a deeper, more meaningful engagement with the cosmos, one driven by wonder rather than worry. It allows everyone to appreciate the true marvel that we, from our tiny planet, can detect, measure, and comprehend the rhythmic heartbeats of these city-sized stellar corpses from across the galactic abyss. That is a story far more incredible and inspiring than any fictional tale of cosmic doom. Beyond the pages of scientific journals and the data from radio telescopes, neutron stars have ignited the imaginations of storytellers, becoming powerful symbols and settings in our shared cultural landscape. They frequently appear in science fiction not just as background elements, but as central, awe-inspiring characters that embody the sublime danger and mystery of the cosmos. One of the most brilliant and scientifically grounded explorations is Robert L. Forward's classic novel, Dragon's Egg. In this fascinating thought experiment, Forward places a species of intelligent life, the Chela, not on a planet, but on the surface of a neutron star. Their entire civilization, from tool use to advanced technology, evolves and passes in the span of just a few minutes from our external perspective, all due to the incredible time dilation caused by the star's immense gravity. This isn't just a wild fantasy. Forward, a renowned physicist himself, built the concept on real scientific principles, crafting a world where the laws of physics as we know them are stretched to their absolute limit to explore themes of communication, relativity, and the very nature of consciousness. It's a perfect example of how science fiction can take a complex astrophysical concept and transform it into a gripping narrative that makes abstract theories tangible and emotionally resonant. This cultural fascination extends far beyond literature. In blockbuster films and popular video games, neutron stars are often depicted as the ultimate cosmic hazard, a navigational nightmare or a destructive force of nature. Their intense gravity wells might serve as a plot device, threatening to tear spaceships apart, or their powerful magnetic fields could be the source of a universe-threatening energy burst. While these portrayals often take dramatic license, compressing light years of distance and decades of time into a single thrilling scene, they serve a vital purpose. They introduce millions of people to these incredible objects, seeding a basic familiarity and sparking an initial, "What is that?" curiosity that can lead to deeper exploration. A viewer might first encounter a neutron star in a game, only to later seek out a documentary or an article to learn the real science behind the pixelated spectacle. This gateway effect is invaluable, transforming cold, distant facts into elements of adventure and wonder. However, this relationship between science and fiction is a two-way street. While storytellers draw inspiration from astrophysics, the creative concepts they dream up can, in turn, influence and inspire real scientific thought. The speculative biology of Dragon's Egg, for instance, forces a consideration of how life might arise under conditions we would never have previously considered. It pushes scientists to ask "what if?" in new ways, challenging assumptions and expanding the boundaries of fields like astrobiology. The imaginative technologies portrayed in media, perhaps a spacecraft using a pulsar's beam for navigation, can sometimes seed ideas that researchers playfully explore in thought experiments or use to illustrate principles to students. This creative cross-pollination doesn't validate the fiction as fact, but it does enrich the scientific culture, encouraging a mindset of openness and boundless curiosity. It is crucial, of course, to maintain a clear distinction between the compelling fiction and the uncompromising reality. As thrilling as the idea of neutron star aliens may be, the actual environment on or near one is unequivocally lethal to life as we understand it. The crushing gravity, the intense radiation, the searing temperatures, and the powerful magnetic fields would dismantle any known complex molecule instantly. The surface is not a solid landscape but a likely smooth, impossibly dense sea of atomic nuclei. Recognizing this doesn't diminish the stories. Instead, it allows us to appreciate them for what they are: brilliant exercises in imagination that use the canvas of real science to explore human themes rather than literal blueprints for reality. This beautiful interplay between the creative arts and hard science ultimately builds a broader and more passionate bridge between the research community and the public. When a concept moves from a textbook to a movie screen, it ceases to be an abstract idea and becomes a shared experience. This cultural resonance fosters a sense of wonder and ownership, which in turn builds vital public support for the often expensive and long-term work of scientific discovery. People are more likely to value and fund the exploration of things they feel connected to, and popular culture provides that initial connection. So the next time you see a neutron star lighting up the silver screen or serving as the backdrop for a virtual adventure, take a moment to appreciate the real cosmic marvel behind the story: a city-sized fossil of a dead star spinning in the void, its rhythmic pulses whispering secrets across the light years. Yet the story of Jocelyn Bell Burnell and the Pulsar discovery brings us to another profound ethical dimension, the question of credit and recognition in scientific achievement. Her experience is far from an isolated historical footnote. It highlights systemic patterns where the contributions of junior researchers, women, and minorities can be overlooked or minimized. The initial Nobel Prize omission, while later widely acknowledged as an injustice, serves as a powerful reminder that the process of discovery is rarely the work of a single individual, but rather a collaborative effort built on the dedication of many. This raises ongoing questions about how we assign value, how we ensure equitable credit, and how we mentor the next generation to create a more inclusive scientific culture. It challenges institutions and prize committees to look beyond seniority and actively recognize the diverse array of talent that drives progress, ensuring that the story of discovery accurately reflects all those who helped write it. Furthermore, astrophysicists carry a responsibility for how their work is communicated and understood by the public. In an era of misinformation, complex concepts like neutron stars can be sensationalized or misunderstood, leading to unnecessary fear or false expectations. Scientists must therefore engage in clear, honest, and accessible outreach, translating their awe-inspiring findings into narratives that educate and inspire without distorting the truth. This also involves a duty to counter pseudoscience and explain the rigorous, evidence-based nature of their work, fostering a society that values critical thinking and rational discourse. The goal is to share the wonder of the cosmos in a way that is both accurate and empowering, inviting everyone to appreciate the universe without requiring them to sacrifice scientific literacy. There is also an environmental cost to consider, particularly as astronomy enters an era of increasingly large-scale facilities. The construction and operation of massive radio telescope arrays, space observatories, and supercomputing centers consume significant energy and resources. While the scientific returns are immense, the community has an ethical obligation to minimize this footprint wherever possible. This can involve powering facilities with renewable energy, designing more efficient cooling systems for data centers, and continually assessing the ecological impact of new projects. The pursuit of knowledge about the universe should not come at the expense of irreparable harm to our own planet. A sustainable approach to exploration ensures that our quest to understand the stars does not blind us to our responsibilities here on Earth. Ultimately, these ethical considerations are not peripheral concerns but are central to the very practice of science. They remind us that astrophysics, for all its grandeur, is a profoundly human endeavor. It is conducted by people, funded by societies, and its fruits are shared with all of humanity. By consciously reflecting on the resources we use, the credit we assign, the stories we tell, and the world we affect, we integrate a deeper moral compass into our exploration. This broader perspective ensures that our journey to decode the cosmos is conducted with not only intellectual rigor, but also with wisdom, integrity, and a profound respect for both our planet and the people who call it home. The pulse patterns of neutron stars may tell us about the laws of physics, but it is our ethical choices that will define the legacy of our curiosity for generations to come. Imagine having a powerful radio telescope at your fingertips without ever leaving your home. This is the reality for thousands of volunteers around the world who are actively participating in the search for and study of neutron stars through citizen science projects. One of the most impactful of these initiatives is Einstein at Home, which harnesses the spare processing power of personal computers to sift through mountains of data from observatories like the Arecibo Observatory and the Very Large Array. When you sign up for the project, your computer downloads small chunks of radio telescope data and analyzes it during its idle moments, searching for the faint, telltale signature of a pulsar's rhythm amidst the cosmic static. This distributed computing model creates a virtual supercomputer made up of millions of devices owned by everyday people, all working in concert to tackle problems too vast for any single research institution to handle alone. The success of this approach is not just theoretical, it has produced tangible, exciting discoveries. Volunteers with Einstein at home have co-authored scientific papers after identifying dozens of previously unknown pulsars, including some exotic systems like a rare double neutron star binary. These aren't just minor footnotes in astronomy textbooks, they are significant contributions that provide new laboratories for testing fundamental physics. The process beautifully inverts the traditional model of scientific discovery. Instead of a small team of experts working in isolation, it's a global, collaborative effort where a teacher in Brazil, a student in Germany, and a retiree in Japan can all play a direct role in cutting-edge astrophysics research simply by running a program on their laptop. This model proves that scientific progress is no longer the exclusive domain of those with advanced degrees and access to multi-million-dollar facilities. For those with a more hands-on inclination, the world of amateur radio astronomy offers another pathway to contribution. While observing pulsars requires specialized equipment, it is not out of reach for dedicated enthusiasts. With a purpose-built radio telescope, which can sometimes be built or assembled from kits, amateurs can participate in timing campaigns. By carefully recording the arrival times of pulses from known pulsars over weeks and months, they can help professional astronomers monitor for rotational glitches, timing noise, or other changes in behavior. This long-term, consistent monitoring is incredibly valuable to large observatories, which have limited time to dedicate to any single object. The collective efforts of a network of amateur observers can provide a continuous stream of data that would be impossible to gather any other way, creating a vital early warning system for when a neutron star does something unexpected. The barrier to entry for this kind of work is lower than ever, thanks to a wealth of educational programs and open-source online resources. Universities and research organizations frequently offer free online courses that teach the fundamentals of pulsar astronomy and data analysis. Platforms like Zooniverse host a variety of projects where anyone can learn to identify patterns and classify data through a user-friendly web interface, no download required. Furthermore, online communities and forums have blossomed, where newcomers can seek advice from seasoned amateurs and professionals alike. This supportive ecosystem fosters a truly global community of enthusiasts, united by a shared passion for unraveling the mysteries of the cosmos. It demystifies the scientific process, showing that it is built on careful observation, persistent curiosity, and collaborative problem-solving skills that anyone can develop. This widespread democratization of science represents a profound shift in how knowledge is created. It empowers individuals, giving them a direct stake in the process of discovery and a tangible connection to the grand questions about our universe. It blurs the once rigid lines between professional and amateur, creating a continuum of engagement where a dedicated volunteer can possess expertise that rivals that of a career academic in a very specific niche. Most importantly, this collaborative model accelerates the pace of discovery itself. It leverages the collective power of human curiosity, proving that the next great breakthrough might not come from a lone genius in a lab, but from the combined efforts of countless curious minds around the world, all contributing their time, their processing power, and their passion to the collective endeavor of understanding the stars. Beyond the raw data and profound physics, neutron stars command our attention for another, deeply human reason: their breathtaking, almost surreal beauty. This isn't the gentle beauty of a sunset or a nebula's glowing clouds. It is a stark, violent, and sublime beauty born from the most extreme conditions the universe can forge. Picture the magnetic field lines surrounding a magnetar, trillions of times stronger than Earth's, not as invisible forces but as dynamic structures. They would appear as a colossal, tangled web of energy, crackling with intense radiation and creating permanent, planet-sized auroras that dance across the star's solid iron surface in a terrifying and magnificent light show. Then add the pulse, the relentless, rhythmic beacon that slices through the interstellar darkness with clockwork precision. This isn't a random flicker, it is a cosmic heartbeat, a precise strobe of energy that transforms the neutron star from a static object into a living, breathing entity in our observations, a lighthouse guiding us through the darkest shores of space. This inherent splendor has sparked a fascinating and vital collaboration between scientists and artists, a fusion of disciplines that brings these distant wonders to life in ways a graph of data never could. Researchers provide the hard numbers, the precise spin rates, the magnetic field strengths, the simulated densities from supercomputers. Artists then take this information and translate it into stunning visualizations and animations that our minds can truly grasp. For instance, simulations of two neutron stars merging are not just crucial for physics, they are a source of awe-inspiring art. Supercomputer renderings show the final moments of the dance as the two ultra-dense spheres spiral together, their surfaces distorting under immense tidal forces before erupting in a blinding, asymmetrical explosion of light and ejected matter. The resulting kilonova is visualized as a magnificent, expanding cloud of newly forged heavy elements, glowing in vibrant hues of gold, blue, and red, a visual representation of the very origin of the elements that make up our world. These are not mere artists' impressions, they are data-driven portraits, allowing us to witness events that are otherwise hidden in a flash of gravitational waves and a burst of gamma rays. This artistic interpretation does far more than just look pretty. It serves a critical role in public engagement and education. A complex mathematical equation describing a pulse profile may be intelligible to a handful of specialists, but a sonification that lets us hear that pulse as a deep, rhythmic drumbeat, or a visualization that shows the beam sweeping through a nebula, makes the science immediately accessible and emotionally resonant. It transforms abstract concepts into experiences. Museums and planetariums use these creations to transport visitors to the surface of these alien worlds, fostering a sense of wonder that pure data alone might not inspire. This process reminds us that science and art are not opposing forces. They are two different languages describing the same universe. One uses mathematics to understand its laws, and the other uses imagery and sound to convey its meaning and emotional impact. They are complementary, two sides of the same human drive to explore, understand, and share what we find. There is also a profound beauty to be found in the underlying order itself. The mathematical equations that predict the timing of a pulsar's flash to nanosecond accuracy over decades possess an elegance and harmony that many scientists describe as beautiful. The way Einstein's field equations perfectly describe the orbital decay of the Hulse-Taylor binary pulsar through gravitational wave emission has a breathtaking simplicity and power. This is a beauty not of color and light, but of logic and consistency, a deep, structural beauty that suggests the universe is not random chaos, but a cosmos, a system ordered by elegant, discoverable rules. By celebrating both forms of beauty, the visual and the mathematical, we enrich our understanding on every level. we appeal not just to the analytical mind, but also to the heart and the imagination, inspiring a new generation of thinkers, dreamers, and explorers who see that the pursuit of knowledge is also a journey into the sublime. It's a captivating thought, isn't it, that the perfectly timed pulses from a neutron star, which so precisely mimic an artificial beacon, could actually be one. This idea isn't just science fiction. It was the very first reaction of the astronomers who discovered them. When Jocelyn Burnell first detected that steady, repeating signal in 1967, the notion of little green men was a serious, if fleeting, possibility. The signal was just too perfect, too engineered looking. This moment in history perfectly illustrates the fascinating intersection between the study of neutron stars and the search for extraterrestrial intelligence, or SETI. It forces us to ask a profound question. In a universe filled with natural wonders, how do we recognize something that is truly artificial? This has led to some truly imaginative speculation. Could an advanced civilization, one that has mastered interstellar travel, use pulsars as a kind of galactic lighthouse system? The concept is compelling. These cosmic clocks are incredibly stable and visible across vast distances, making them ideal reference points for plotting a course through the Milky Way. A spaceship's navigation computer could theoretically use the unique pulse patterns of several different pulsars to triangulate its position anywhere in the galaxy with phenomenal accuracy, much like how we use GPS satellites here on Earth. Some have even theorized that a sufficiently advanced society might not just use pulsars, but could actually create or modify them, engineering a star itself to broadcast a specific, purposeful signal. Perhaps the pulses could be subtly altered to carry information, embedding a message within the rhythm itself, a cosmic Morse code waiting to be deciphered. However, it is crucial to emphasize that there is absolutely no evidence to support these ideas. The scientific consensus remains that pulsars are entirely natural phenomena, the products of well-understood, albeit extreme, astrophysics. But that doesn't render the speculation useless. In fact, it provides an incredible service to the SETI community. The meticulous study of pulsars has given us an exhaustive catalog of what complex, yet natural, signals look like. We now understand the physics that creates their pulse shapes, their timing glitches, their frequency drifts, and their polarization. This deep knowledge acts as a powerful filter. When SETI researchers scan the skies with radio telescopes, they can now much more easily recognize and eliminate the countless false positives that come from pulsars and other astrophysical sources. This allows them to focus their search on signals that truly stand out from the cosmic background, those that exhibit anomalies that cannot be explained by any known natural process. This relationship is a beautiful example of how pure, curiosity-driven science in one field can provide indispensable tools for another. Astrophysics didn't set out to aid the search for aliens, but in decoding the language of neutron stars, it has inadvertently given SETI a key to distinguishing nature's symphony from a potential soloist. It highlights a fundamental principle of the search: the importance of first understanding the universe's natural vocabulary before we can hope to identify a word that seems deliberately spoken. This rigorous methodological approach protects the field from the pitfalls of premature excitement and ensures that any potential future discovery would be based on irrefutable evidence. Ultimately, while a neutron star's surface with its crushing gravity, intense radiation, and searing temperatures is among the most hostile environments imaginable and utterly incompatible with life as we know it, its signal serves a different purpose. It stands as a testament to the incredible diversity and ingenuity of nature, It reminds us that the universe can produce phenomena so strange and so precise that they border on the artificial, expanding our concept of what is possible. This realization fosters a crucial open-mindedness, a willingness to consider possibilities that might initially seem outlandish. It encourages us to keep listening, to keep questioning, and to remain awestruck by the fact that sometimes the truth, a spinning, city-sized ball of neutrons, is every bit as wondrous as fiction. Sometimes the most profound technological leaps begin not in an engineering lab, but with a question about the distant cosmos. The relentless, perfect ticking of pulsars is more than a scientific curiosity. It's a natural resource of unimaginable precision, and it has inspired a vision for the future of navigation that could one day take spacecraft to the farthest reaches of our galaxy. The concept is known as pulsar-based navigation, or XNav, and it works much like GPS but on an interstellar scale. Our current GPS system relies on a constellation of satellites in Earth orbit, each containing a precise atomic clock. A receiver on the ground calculates its position by measuring the tiny time delays in signals received from multiple satellites. Now, imagine replacing those human-made satellites with nature's own millisecond pulsars scattered across the galaxy. Each one is a lighthouse with a unique pulse signature, and its position on the celestial sphere is known with exquisite accuracy. A spacecraft equipped with an X-ray telescope could detect the pulses from several of these cosmic clocks. By comparing the arrival times of these pulses against their predicted times based on a known reference location, the spacecraft's computer could triangulate its own position in space, completely independent of any Earth-based system. The incredible stability of millisecond pulsars means this system wouldn't suffer from the tiny drift that plagues even our best atomic clocks over long periods. For a probe journeying to another star, a journey that could take centuries, an onboard pulsar navigation system would provide a self-contained, autonomous, and eternally reliable way to know exactly where it is on the grandest map of all. This isn't just theoretical. NASA's NICER/Sextant experiment on the International Space Station has already successfully demonstrated the core technology, using X-ray pulses from pulsars to determine the station's position in orbit with remarkable accuracy, proving that this once fanciful idea is firmly within our grasp. The technological fallout from neutron star research extends far beyond the realm of navigation, reaching right into the heart of modern medicine. To understand the mind-bending magnetic fields of magnetars, scientists must push the boundaries of electromagnetism and materials science. This research into generating and measuring these ultra-strong fields has a direct and life-saving parallel in the development of magnetic resonance imaging, or MRI, machines. The core of every hospital MRI is a powerful superconducting magnet, and the relentless drive to make these magnets stronger and more stable to see finer details inside the human body draws from the same pool of physics that helps us comprehend the forces at work on a neutron star. Furthermore, the challenge of processing the faint, complex signals from pulsars has driven innovation in signal processing algorithms. The techniques developed to clean up noisy radio telescope data and extract the pristine pulse signal from the background static have found powerful applications in enhancing the clarity of medical images from MRIs to CT scans. By improving the algorithms that filter out interference and sharpen details, astronomers have indirectly helped doctors detect smaller tumors, identify finer neurological structures, and make more accurate diagnoses, demonstrating that the quest to understand the most extreme objects in the universe can yield tools that heal and protect life right here on Earth. Perhaps one of the most unexpected spin-offs lies in the realm of pure computing. Neutron stars are fiendishly complex to model. Simulating their interior requires simultaneously solving the equations of general relativity, quantum mechanics, plasma physics, and nuclear physics, a computational problem of nightmarish difficulty. To even attempt this, scientists must employ the world's most powerful supercomputers and develop radically efficient new algorithms to make the calculations feasible. The code written to model the flow of a superfluid inside a neutron star crust or the merger of two of these ultra-dense objects doesn't just stay in astronomy departments. These advanced computational methods, particularly in the field of fluid dynamics and magnetic field modeling, have been adapted and applied to a host of other challenges. They are used to design more efficient wings for aircraft, simulate the flow of blood through arteries for medical research, model global climate patterns with higher fidelity, and even predict the behavior of financial markets. The need to understand the universe has consistently acted as a catalyst, pushing the limits of our computational capabilities and forcing us to invent better, smarter ways to process information, with benefits that ripple out across countless industries and disciplines. This pattern of curiosity-driven discovery leading to unexpected practical benefit is a powerful argument for the value of fundamental science. When scientists first began studying pulsars, they were not trying to build a better navigation system or improve medical imaging. They were driven by a simple desire to understand a strange new signal from the cosmos. Yet, by following that curiosity without a predetermined practical goal, they unlocked a treasure trove of technological innovation. It's a story that has repeated itself throughout history, from the discovery of electromagnetism to the invention of the laser. Investing in the basic, seemingly abstract quest to understand neutron stars and other cosmic phenomena is not a diversion from practical needs. It is one of the most powerful ways to seed the technological landscape for the future. It builds the foundational knowledge and develops the advanced tools that will solve the practical problems of tomorrow, problems we cannot even anticipate today. The tangible impact of this research underscores a profound truth. When we reach for the stars, we don't just learn about the universe, we also learn how to build a better future for ourselves. Think about the most precise clock ever built by human hands, an atomic clock so accurate it might lose or gain less than a single second over the entire age of the universe. Now imagine a natural object in space that can rival that precision, a celestial timepiece that has been ticking with unwavering regularity for millions of years. This is the incredible reality of a millisecond pulsar. Their rotational stability is so profound that it transforms them from mere astronomical curiosities into the most reliable natural clocks in the entire cosmos. This isn't just a minor detail. It's a property that allows scientists to use these distant stars as tools for experiments of almost unimaginable scale and sensitivity, turning the galaxy itself into a grand laboratory for fundamental physics. One of the most thrilling applications of this cosmic timekeeping is in the hunt for gravitational waves. We've already discussed how pulsar timing arrays work, but the sheer precision required is worth emphasizing again. To detect the faint ripples in spacetime caused by the slow inspiral of supermassive black holes, astronomers need to measure the arrival time of pulses with an accuracy down to a few tens of nanoseconds over a decade or more. This is like timing a marathon runner's every step with a stopwatch that is accurate to a few billionths of a second for years on end. The fact that these natural clocks, born from stellar cataclysms, can provide this level of consistency is nothing short of miraculous. It allows us to sense distortions in the fabric of the universe itself, distortions so tiny they change the distance between stars by less than the length of a football field. By carefully monitoring a network of these pulsars, we are essentially building a galaxy-sized interferometer using the rhythms of dead stars to listen to the deepest bass notes of the cosmic symphony. But the applications go even further, probing the very laws of nature themselves. By comparing the ticking rate of these pulsar clocks against the best atomic clocks on Earth over long periods, scientists can perform exquisite tests to see if the fundamental constants of the universe are truly constant. Take the fine structure constant, for instance. This number, which governs the strength of electromagnetic interactions, is a cornerstone of physics. If this constant were found to be slowly changing over billions of years, it would revolutionize our understanding of the cosmos, suggesting that the laws of physics themselves are not immutable but evolve over time. The steady pulse of a millisecond pulsar, which has been traveling through space for eons, provides a unique way to check this. Any drift in the constant would subtly affect the propagation of light and the behavior of matter in ways that would minutely alter the observed pulse arrival times over cosmic epochs. It's a test of stunning precision, using the heartbeat of a neutron star as a reference point against which to measure the potential evolution of reality's rulebook. This incredible work bridges two seemingly disconnected fields, astronomy and metrology, the science of measurement. Metrologists spend their lives crafting ever more perfect standards for the second, the meter, and the kilogram. Now they find that some of the most perfect standards are located thousands of light years away, spinning in the void. The idea of a pulsar second or a cosmic time standard is not just a fantasy. There are serious proposals for defining units of time based on the observed periods of these stellar clocks, creating a system that would be independent of Earth and could be used for navigation anywhere in the galaxy. This connects our human-scale concepts of time, developed from the cycles of our planet, to the vast, impersonal scales of the universe. It offers a humbling and profound perspective on our place in the cosmos. We are a young species on a small planet, learning to tell time by reading the ticks of distant, ancient stellar corpses. In relying on these stars, we see how humanity is learning to measure the seemingly immeasurable. We are using rhythm to map gravity, using time to explore the constancy of physics, and using the regular spin of a city-sized object to understand the history and fate of the entire universe. Each precise pulse is a data point in the grandest experiment ever conceived, an experiment that asks the biggest questions we can possibly ask, and the clocks are just sitting out there, ticking away, waiting for us to be clever enough to read them. Yet the story of discovery in this field is far more than a tale of isolated genius. It is a powerful narrative of collaboration, perseverance, and the vital importance of opening the doors of science to everyone. While Jocelyn Burnell's detection of the first pulsar is its most famous chapter, it is by no means the only one written by women whose curiosity and dedication have fundamentally shaped our understanding of these cosmic objects. Their ongoing contributions form a continuous thread of innovation, proving that diversity of thought and experience is not just a matter of equity, it is a fundamental driver of scientific progress itself. Consider the work of astrophysicist Victoria Caspi of McGill University, a world-renowned leader in the study of magnetars. Her meticulous research into these intensely magnetic neutron stars has been instrumental in decoding their bizarre and violent behavior. Caspi and her team have used space-based X-ray telescopes to catch magnetars in the act of erupting, analyzing the aftermath of starquakes and giant flares to probe physics in regimes that simply cannot be replicated in any laboratory on Earth. Her ability to design rigorous observing campaigns and interpret complex data has unlocked secrets about the strength of magnetic fields beyond comprehension and the nature of matter under extreme stress. It's work that requires not only brilliant analytical skill, but also immense patience and a creative approach to problem solving, qualities that have cemented her status as one of the most influential figures in modern astrophysics. Similarly, the contributions of Maura McLaughlin at West Virginia University have been pivotal in exploring the population of millisecond pulsars. As a key member of the nanograv collaboration, McLaughlin has dedicated her career to finding and timing these ultrafast, incredibly stable cosmic clocks. Her work is central to the ambitious goal of using pulsars to detect low-frequency gravitational waves, a project that requires exquisitely precise measurements over many years. By helping to build and lead a large, collaborative team focused on this long-term objective, she exemplifies the modern shift in science toward complex, collective efforts. Her research doesn't just advance theoretical knowledge, it pushes the very limits of observational technology and data analysis, developing new tools that benefit the entire field. The achievements of researchers like Caspi and McLaughlin are powerful counterpoints to a historical legacy where women's contributions were too often overlooked or undervalued. The well-known story of the Nobel Prize oversight in the discovery of pulsars is not an isolated incident from a bygone era, but part of a broader pattern that the scientific community is still working to rectify. Despite these historical headwinds, women are now increasingly at the helm of major telescope projects, leading international research collaborations and guiding the next generation as mentors and professors. This shift is not happening by accident. It is the result of conscious efforts to create more inclusive environments, to implement fairer hiring and review practices, and to actively champion the work of scientists from all backgrounds. This progress matters profoundly because it directly enriches the process of scientific inquiry itself. When teams are composed of individuals with diverse life experiences and perspectives, they are better equipped to tackle complex problems from multiple angles and to avoid the pitfalls of groupthink. A question posed from a unique viewpoint can spark a new line of investigation that others might have missed. The story of neutron stars is in many ways a perfect example of this. It is a field built on patient observation, careful analysis, and collaborative interpretation, a process that thrives on the inclusion of many different voices. By ensuring that the scientific community reflects the diversity of humanity, we aren't just being fair, we are maximizing our potential for discovery. We are ensuring that the best and brightest minds, regardless of gender or background, can contribute to the grand human adventure of exploring the cosmos and decoding the rhythmic messages from its most extreme hearts. Now let's push our imaginations to the very edge of known physics and into the realm of the truly speculative. What if the bizarre behavior of a neutron star wasn't just telling us about our universe, but could offer a faint, whispered hint about others? This is the captivating and highly theoretical idea that these ultra-dense objects might serve as portals, not for travel but for inference, into the possibility of a multiverse. The concept of the multiverse suggests that our cosmos might be just one bubble in a vast, frothing sea of universes, each with its own unique set of physical laws and fundamental constants. In some of these other universes, the strength of gravity might be weaker, the nuclear force stronger, or the mass of an electron slightly different. These variations would have dramatic consequences for how a universe evolves and what kinds of objects can form within it. This is where neutron stars become a potential cosmic laboratory for the multiverse. Their very existence and structure are exquisitely sensitive to the precise values of these fundamental constants. For example, the strength of the force that holds atomic nuclei together, known as the strong nuclear force, is perfectly balanced in our universe to allow for the existence of stable neutrons and the complex nuclei that make up our world. If this force were even slightly stronger or weaker in another universe, the entire life cycle of stars would change. A neutron star, that perfect equilibrium of gravity and neutron degeneracy pressure, might not even be possible. Or if it could form, its properties would be radically different. Its maximum mass might be higher, its size might be smaller, or its internal composition might be something we cannot even conceive of. So how could we ever detect such a thing from our lonely bubble? The answer lies in the precision of the pulse. Imagine astronomers, decades from now, have compiled exquisitely detailed data on thousands of neutron stars. Their masses, radii, and pulse patterns are all mapped with incredible accuracy. Now, imagine they find one, just one, that is a true outlier. A neutron star whose mass is far beyond what our models say is possible, or whose pulse profile exhibits a strange, persistent glitch that cannot be explained by any known model of superfluid dynamics or crustquakes. After ruling out every possible error and conventional explanation, a tantalizing, wild possibility remains. Could this object be a relic from a time when the constants of nature were different? Or, in an even more mind-bending scenario, could it be an actual visitor? The concept of a universe metastasis, or a collision between cosmic bubbles in the multiverse, is pure speculation, but it illustrates the kind of thinking that extreme objects can inspire. An anomalous neutron star could be the unique fingerprint of a different set of physical laws, a cosmic accident that arrived in our universe carrying the signature of another. This line of inquiry is the very definition of frontier science. It is currently without a shred of empirical evidence and may forever remain in the realm of theoretical fantasy. But its value is not in its immediate provability. Its value is in its power to motivate. The mere possibility, however remote, that a neutron star could hold such a profound secret drives scientists to make ever more precise measurements. It encourages the development of even more sensitive telescopes and more sophisticated data analysis techniques. It fosters a culture of radical open-mindedness where researchers are willing to ask, what if? In the most expansive ways possible, this is how science truly progresses. The greatest breakthroughs often come from initially dismissing the seemingly impossible and then doggedly pursuing the evidence wherever it leads. The steady, rhythmic pulse of a neutron star is a message written in the code of physics. For now, we are still learning to read the language of our own universe within that code. But the day we find a character we don't recognize, a symbol that doesn't belong, might be the day we get our first glimpse into the cosmology beyond our own. The journey to understand neutron stars doesn't end with this video. In many ways, it's just the beginning. For anyone feeling that spark of curiosity, that desire to dive even deeper into the physics of pulsars, magnetars, and the extreme limits of matter, a universe of educational resources is waiting, most of them just a click away. You don't need a PhD to start exploring. You just need a sense of wonder and a connection to the internet. Leading space agencies are incredible first ports of call. Both NASA and the European Space Agency, the ESA, maintain extensive, free online archives packed with content designed for the public. Their websites feature stunning image galleries from telescopes like Hubble and Chandra, detailed articles written by their own scientists explaining complex concepts in clear language, and even interactive tools that let you manipulate data or simulate cosmic events. They also produce short, engaging documentaries and animations that bring the life cycle of a neutron star to vivid life, making these distant objects feel tangible and real. For those who prefer a more structured learning path, the world of online education has completely democratized access to top-tier astrophysics. Platforms like Coursera, edX, and Khan Academy offer courses created by professors from prestigious universities like Caltech, MIT, and Stanford. You can find introductory courses on astronomy that dedicate entire modules to stellar evolution and compact objects, all the way up to highly specialized classes on general relativity and gravitational waves that use neutron stars as their primary case studies. The best part is that you can often audit these courses for free, learning at your own pace from some of the world's foremost experts without any cost or pressure. If reading is more your style, countless textbooks and popular science books delve into this subject with both authority and captivating prose. Books by authors like Neil deGrasse Tyson, Brian Greene, and the late, great Stephen Hawking take these immensely complex ideas and weave them into narratives that are as accessible as they are profound, often dedicating entire chapters to the strange physics of pulsars and the dramatic stories of their discovery. But learning about the cosmos shouldn't be a solitary activity confined to a computer screen. One of the most rewarding ways to engage is to connect with the vibrant community of amateur astronomers and enthusiasts. Local astronomy clubs exist in most cities and towns, and they are typically filled with friendly, knowledgeable people who are passionate about sharing their love of the night sky. Club meetings often feature guest speakers, including professional astronomers who discuss their latest research. Even more exciting are the organized star parties, where members set up their telescopes in a dark sky location and invite the public to look through them. While you won't see a neutron star itself through an amateur telescope, they are simply too small and distant. You can easily observe the faint, smoky remnants of the supernova that created them, like the Crab Nebula. This tangible connection to the destructive birth of these objects is a powerful experience. Furthermore, many universities and public observatories host open nights where their larger research-grade telescopes are made available for public viewing, offering another incredible gateway to hands-on experience. This widespread accessibility is the true magic of modern science education. It ensures that the wonders of the universe are not locked away in ivory towers or reserved for those with specific academic credentials. A high school student in a rural community can access the same data from the Chandra X-ray Observatory that a professor at Harvard uses. A retiree with a newfound interest in space can join an online course and discuss concepts with learners from across the globe. This democratization of knowledge means that anyone, regardless of their background, age, or location, can become an active participant in the grand conversation about our cosmos. They can move from being a passive observer to an informed enthusiast, capable of understanding the significance of the latest headline about a gravitational wave detection or a new Magnetar flare. This ongoing collective exploration, fueled by widespread education and public engagement, is how we will continue to unlock the universe's deepest secrets, one pulse, one discovery, and one curious mind at a time. Yet beyond the equations and the data, beyond even the gravitational waves and the exotic matter, lies a deeper layer of inquiry that neutron stars force upon us, a layer not of physics but of philosophy. These cosmic extremes are more than just objects of study. They are mirrors reflecting our most fundamental questions about reality itself. Consider the very nature of matter. On Earth, we categorize it into solids, liquids, and gases, states defined by familiar rules. But inside a neutron star, matter is crushed into a form that defies all earthly classification. It is a superfluid that flows without friction, a solid crust 10 billion times stronger than steel, and a core that might be a soup of free quarks. This bizarre reality challenges our most basic intuitions. It forces us to ask, what is matter truly when stripped of all the comfortable properties we know? The neutron star tells us that our everyday experience is a tiny, privileged slice of a much vaster and more alien spectrum of existence, a humbling reminder that the universe is not obligated to conform to human expectation. This confrontation with the unfamiliar extends to our conception of time. In our daily lives, time is a river flowing steadily forward, measured by the ticks of a clock. But a pulsar's pulse presents us with a different kind of time, cosmic time. Its rhythm is so unwavering that it rivals the most precise atomic clocks humanity can build, a stability maintained not by human engineering but by the immutable laws of gravity and angular momentum over millions of years. This isn't just a tool for measurement, it is a physical manifestation of time's regularity on a galactic scale. It connects our fleeting human seconds to the deep, patient ticking of the cosmos, suggesting an underlying order and predictability to the universe that transcends our brief existence. When we listen to a pulsar's beat, we are hearing a metronome that was counting long before life emerged on Earth and will continue long after we are gone. It places our human timeline within a vastly grander narrative, offering a profound perspective on our transient place in the eternal. This inevitably leads to a classic debate in the philosophy of science. Do our models of neutron stars reveal fundamental truths about the universe, or are they merely useful tools that work for now? We have brilliant theories like quantum chromodynamics and general relativity that predict the existence of quark matter and gravitational waves with stunning accuracy. The confirmation of these predictions through pulsar timing can feel like we are uncovering absolute truth, but philosophers caution that a model's success is not the same as proof of its ultimate reality. Our understanding of a neutron star's interior is built on inference and indirect measurement. We cannot go there and scoop up a sample. It is possible that future discoveries will reveal our current models to be incomplete, much like Newtonian mechanics was superseded by Einstein's relativity. This doesn't diminish our achievements. Instead, it frames science as a dynamic, evolving conversation with the cosmos, a relentless pursuit of better approximations rather than a final arrival at absolute certainty. The neutron star, in all its enigmatic glory, thus becomes a symbol not of what we know, but of the endless human quest to know more. Engaging with these ideas does more than just satisfy intellectual curiosity. It nourishes a deeper, almost spiritual yearning for meaning. To contemplate a neutron star is to stand at the frontier of the known and peer into the sublime. It is to grapple with forces of creation and destruction so immense that they dwarf human concerns, yet to also discover an elegant mathematical order that makes the cosmos comprehensible. This intersection of awe and understanding is where science and philosophy meet, where data transforms into wisdom. It reminds us that the drive to explore the stars is, at its heart, a drive to understand our own existence within this vast and mysterious universe. The pulse patterns we decode are not just signals from a dead star, they are part of a cosmic story, and in listening to them, we find a deeper connection to the reality we all share. Our journey into the minds of stars, decoding the pulse patterns of neutron hearts, has taken us from their violent births in supernova explosions to their modern roles as the most precise cosmic laboratories we have ever discovered. We've seen how these city-sized objects, with densities that boggle the mind, serve as natural physics experiments, allowing us to test Einstein's theory of general relativity with breathtaking accuracy, and even listen for the faint ripples of gravitational waves moving through the fabric of spacetime. We've explored the human stories behind the science, from the curiosity that led to their discovery to the collaborative global efforts that continue to unravel their secrets today. These stellar remnants are more than just distant curiosities. They are active participants in the cosmos, influencing the creation of elements, illuminating the behavior of matter under extreme pressure, and reminding us of the beautiful, often violent, processes that shape our universe. They stand as testaments to the fact that the universe is not only stranger than we imagine, but stranger than we can imagine, yet it is also knowable, understandable, and filled with a deep, resonant order. This exploration underscores a profound truth about our place in the cosmos. We are a young species on a small planet, yet through our ingenuity and relentless curiosity, we can reach out across the light years to decipher the rhythms of these incredible objects. The story of neutron stars is a story of connection, connecting the very large to the very small, the laws of the quantum world to the force of gravity, and human questions to cosmic answers. It's a narrative that blends the cold, hard facts of physics with the warm, human drive to explore and understand. As Carl Sagan so perfectly put it, somewhere, something incredible is waiting to be known. That sense of wonder, that anticipation of discovery, is what fuels this entire endeavor. It's what compels us to build ever larger telescopes, to develop more sensitive detectors, and to keep looking up at the night sky with a sense of awe and possibility. The universe is filled with mysteries waiting for their moment of revelation, and the next great discovery could be just one observation away. We encourage you to carry this sense of wonder with you. Keep looking up, keep asking questions, and keep sharing in the joy of discovery. The cosmos is a story that belongs to all of us, and every new piece we learn adds to our collective understanding. If this journey into the hearts of neutron stars has sparked your curiosity, consider subscribing to our channel for more deep dives into the universe's greatest mysteries. We'd love to hear what cosmic phenomenon captivates you most. Let us know in the comments what you'd like us to explore next. Thank you for joining us on this incredible adventure through space and time.